The MSP430 was designed from its conception to be an ultra-low power device. Some applications using MSP430s run for 10 years on a single button cell battery, and that lifetime is determined by the life of the battery rather than the current draw of the MSP430. In previous sections, we've deliberately ignored low power considerations to keep things simple. But in section 6, you'll dive into the ultra-low power capabilities of the MSP430.
There are a number of low power modes for the MSP430, as shown here. The top in the list, of course, is the active mode, with the CPU active and all enabled clocks up and running. As you go down the list, and you can take the list and compare it to the diagram on the lower left, from LPM 0, we start to turn off the CPU and the M clock. With LPM 1, we start to disable the DCO. With LPM 2, we disable the DCO and the A clock is still on. At LPM 3, all those things are off except for the A clock. The DC generator is turned off. And by the time you get to LPM 4, basically everything inside the part is turned off, including the DC generator. You need something to wake you up, and depending on what you have running in terms of clocks, you have that peripheral that's running on that clock available to wake you up. If you're in LPM 4, for example, with all the clocks disabled, basically the only thing that's going to wake you up is some kind of interrupt from the outside world. If you're running under LPM 2 or LPM 3 where you have the A clock running, well then you could wake up on some kind of timer or something, some peripheral that's running on the A clock. Of course, as you move up the list, the higher the current, the higher the power that the device is drawing. So typically what you do is you decide which low power mode you can run in based on what you need in order to wake up from low power mode. If you don't need anything to wake you up and you're waking off of some external interrupt, then you can go all the way down to LPM 4 and get the absolute lowest power possible on the MSP430. Low power operation on the MSP430 follows a couple of basic rules. One is to minimize the instantaneous current draw. Try to keep the number of peripherals and things that you're running inside the part as few as possible, and to maximize the time spent in the lowest possible power modes. You know, the MSP430 is inherently low power, but the way you implement your design has a huge impact on the power efficiency that you extract from that device. Properly working with the low power design techniques can make all the difference in the world. For instance, down here at the bottom, and this diagram is just a little bit hard to understand. If you look, there's the MSP430 running off of the clock crystal on the left, running the A clock. Well, in this case, that's always on. A 32 kilohertz crystal, running our A clock, running our low power peripherals. The M clock and the CPU can wake up on demand and run whatever you need to run quickly and go back to sleep. That's reflected in the diagram on the right, the instant on clock, that we're down in the 1 microamp range when we're sleeping. We wake up, we run at 230 microamps or whatever it is to draw current. We do our thing, we do our computation for a short period of time, and we go back to sleep. So we're maximizing the time that we spend in sleep modes, or our lowest possible power modes. Of course, current draw increases as you increase the VCC, as you increase the CPU clock speed, and as you increase the temperature. Of course, the VCC is a factor of how fast you intend to run the part. Your CPU clock speed can also be a factor of their lowest possible battery voltage that you can run the part at, as well as the time it takes to do whatever you're trying to do. Slowing down the M clock can reduce the instantaneous power, but you're going to increase the active duty cycle. So it's possible to nullify the power savings. Typically, there's some kind of the ultra-low power sweet spot that maximizes the performance for the minimum possible current draw. Often that's around 8 megahertz M clock. It may be down as low as 1 megahertz. It's best to experiment with your application and see what's the absolute best. Of course, all the way down to 2.2 volts, you have full operation of the entire part. You can use the in-system programmability, the flash, all the way down to 2.2 volts. Of course, if you don't need that, you can slide down to 1.8. That lowers your maximum possible M clock, but if you don't need that fast, then that's a good choice. So the typical rule is to optimize your core voltage for whatever you choose as the M clock speed. So that takes us back to this diagram of the possible M clock speeds versus the VCC. Remember, matching your needed clock speed with required VCC will get you down to the lowest possible power. And to remember that if you have your power slide underneath the VCC required for your selected clock speed, then you can get into unreliable execution. This can often happen at the tail end of a battery, where the battery is discharging and the voltage on it goes down below the voltage that you need to run your M clock. An external LDO can prevent that, but may cause you to have to run on a slightly higher voltage battery. Pin muxing may seem like an odd topic to put here in the low power section, but it plays directly into the next slide, that we need to know exactly what every pin on the device is doing and whether or not it's unintentionally costing us some power. If you take a look at the diagram of the DIP package in the upper right, you can see that some of the pins have 2 functions. Some of them have as many as 4 functions on them. Those functions are determined by the diagram there on the left-hand side, the terminal functions. So one single pin could be a port 1 pin 0 general purpose digital I/O. It could be the timer 0 clock signal. It could be the A clock signal output, and it could be the ADC10 analog input. The top selection in that list is the default selection. If you look at the bottom diagram, the port 1 pin functions, this is how you make the selection for what those pin functions are. If you have a pin that's not going to be connected in your design, you want to make sure that that pin is a GPIO pin, a general purpose I/O pin, and then you're going to deal with it like I'm going to show you on the next slide. So it's important to make your selections for the peripherals that you want to bring to the outside world, and then those that end up unused, we're going to make those GPIO, and then we'll see on the next slide how to deal with that. Let's take a look at how to deal with unused pins. If you have a digital input pin that's just sitting there not connected to anything, it's subject to shoot-through current. Input voltage anywhere between the VIL and VIH can cause shoot-through if the input's allowed to float or left unconnected. This can cause the device to use significant amounts of current. The CMOS inputs on the MSP430 and any other CMOS device only draws current if it's being switched. If it's switched to a certain one state or the other, to a 0 or 1, there's no current being used. So if you have a port I/O that's unconnected, you should drive it to an output and then drive it to a 0 or a 1. You could also drive that to VCC or ground by an external device if you want to, but that can also cost your design and reduce your flexibility. You can use a pull-up or pull-down resistor. Remember, every one of these pins has a pull-up or pull-down resistor, but the possibility exists to draw some kind of parasitic current through that. So typically what we do is to take any unused I/O, set it up to an output, and then put a 1 or a 0 on that output.
In Lab 6, you're going to modify the code to use the MSP430's low power modes. If you have a digital multimeter that can measure the current, you can use it to verify our results. When you're done, the code will use a small fraction of the power that it did when you started. If the launch had a voltage regulator on it, you could lower the power even further, but that exercise will be left for later. So let's create a new project by clicking File, New, CCS Project. Make the selections as shown below in your workbook. If you're using the 2231, make sure you make the appropriate choices for that part. Make sure to click Empty Project when you're done and click Finish. For the source file, we're going to use the solution file from the last lab exercise as the starting point for this lab exercise. So open up the lab5finish.txt file using File Open File. That's in the Lab 5 Files folder. Go ahead and copy all of the code from the Lab 5 Finish text file and paste it into main.c, making sure that you erase the original contents of main. This is going to be the starting point for this lab exercise. Go ahead and close the lab5finish.txt file. It's no longer needed. Remember, if you're using the 2231, make sure you make the appropriate change to the header file at the top of main.c. If you have a digital multimeter, a DMM, you can make the following measurements. Otherwise, you're going to have to take our word for it. The sampling rate of 1 second is probably too fast for most meters to settle, so we're going to extend that time from 1 to 3 seconds. In step 4, find and change the following lines of code. In config timer A2, in that function, change the CCR 0 equals 12,000 to 36,000. Then in the timer ISR, change the CCR 0 plus equals 12,000 to CCR 0 plus equals 36,000. In step 5, the current drawn by the red LED is going to throw off our current measurements. We want to measure the current drawn by the MSP430, not the LEDs. So comment out the last two P1 outlines inside the while loop. As a test, build, load, and run the code. If everything's working properly, the green LED should blink about once every 3 seconds. And let's take a look at that. And it's working properly. When you're done, halt the code, click the Terminate button, and return to the edit perspective. So now go ahead and turn on your multimeter and measure the voltage between VCC and ground at header J6. You should have a value of around 3.6 volts. So we're getting 3.56, 3.57 volts. That's about right. Go ahead and build, load, and run the code again. If everything's working properly, right, the green LED should blink once every 3 seconds. If you're interested in the state of the MSP430 registers, click on View Registers. You can expand any of the peripheral registers to see how they are set up. If you see unable to read in the value column, try suspending or halting the code. The emulator can't read memory or registers while the code is executing. Poke around in there for a while, and when you're done, click the Terminate button and return to the editing perspective. Now in step 9, we're going to completely isolate the target area from the emulator, except for the ground. That will make sure there's no additional current that's flowing into the emulator section. That'll throw off our current measurements. So remove all 5 jumpers. I'm going to remove the voltmeter here. Remove all 5 jumpers from the header on J3 and set them aside where they won't get lost. Set your multimeter to measure current, and then connect the DMM, the red lead on the top and the black on the bottom here on the VCC connections of J3. Go ahead and press the reset button on your LaunchPad board. If your multimeter has low enough effective resistance, the green LED on the board will flash normally. And let's take a look for that. it's flashing properly. And you should see a reading on the multimeter. If not, the resistance of your meter is too high. Oddly enough, we found that low-cost DMMs work very well. You can find one of these online for less than $5 US. Now we can measure the current drawn by the MSP430 without including the LEDs and emulation hardware. Remember that if you turn off your DMM, you're going to turn off the MSP430. This is going to be our baseline current reading. Measure the current between blinks of the green LED. Well, we're getting a value of 103, right around 103 microamps. Go ahead and record your measurement in the space provided. Once you have that, remove the meter leads, carefully replace the jumpers on J3. Remember, if you forget to put these jumpers back in place, when you try to do emulation with Code Composer, it will say that it can't find your emulator. And you could just put these back and then hit retry. So we need to make sure that all of the device pins are configured to draw the lowest possible current. Referring to the device datasheet and the LaunchPad board schematic, you can notice that port 1 defaults to GPIO. Only port 1 pin 3 is configured as an input to support the push button switch S2. All the rest are configured as outputs. P2 pin 6 and P2 pin 7 default to crystal inputs. We're going to configure them as GPIO unless you have a system that you've already soldered in the crystal. So in step 10, rename the config LEDs function, declaration, and call to config pins. So there should be 3 places in the code to do that. And I'm going to mention here that we've just switched our capture method. So our typist here is going to switch between the person who's driving the system is going to switch between the PDF and Code Composer Studio. So in step 11, delete the contents of the config pins function and insert the following lines. P1 dir equals not bit 3 and P1 out equals 0. So we're setting just one of those to be an input. The rest, so sending a 0 to an input pin is meaningless. That sends zeros to all the rest of the output pins. In step 12, there are 2 pins on port 2 that are shared with the crystal X in and X out. In this lab, we're not using the crystal, so even if you have the crystal on there, that's okay. So we're going to set these pins to be GPIO. The device datasheet indicates that P2 cell bits 6 and 7 should be cleared to select GPIO. Add the following code that's shown in the book, the following 3 lines, to the config pins function. That's P2 cell to select the and what we're doing on them, GPIO. P2 dir selects the direction of those to output, and P2 out puts 0 on both of those. So at step 13, at this point, your code should look like the code below and the code on your screen. We've added the comments to make it easier to read and understand in the book. Click on the Save button on the menu bar to save the file. It's possible that the middle line of code will result in an integer conversion resulted in truncation warning. You can ignore that. So that takes us to step 14, build, load, and run the code. So we should be able to take a look back at the board, and it's blinking once every 3 seconds. What I'm going to do, go ahead and press Terminate in Code Composer to return to the editing perspective. Then I'm going to remove all of the jumpers on J3, connect up the meter, and I believe we had about 103 microamps before, and we've got about the same now. That's not unexpected. There's no real savings here. There's not much happening on the board to cause any real issues. Regardless, this is one of the things that you need to keep in mind. You need to terminate unused I.O. properly. So what I'll do at the end of that is go ahead and remove the meter leads and put the jumpers back on J3 to reconnect to CodeComposer. So that takes us to an analysis section here. You should see a graph on the screen. The current consumption of the 2553 and the 2231, if you're using it, looks something like the graph below, or ignoring the LED. The graph isn't the scale in either axis, and our code departs from this timing a little bit. With the CPU active, we were drawing 103 microamps all the time. The current needed for the ADC10 reference is 250 microamps, and that's on for 33 microseconds out of each 3-second sample time. The conversion current of 600 microamps is only needed for 3 microseconds. We don't have that code timing right now, but we'll do that later. If you could limit the amount of time that the CPU is active, the overall current requirement would be significantly reduced. Of course, always refer to the datasheet for design numbers, and remember, the values we're getting in the lab exercise can be slightly different from what you're going to get. So that takes us to step 16. The majority of the power being used by this application is being spent in the while loop waiting for an interrupt. We can place our device in a low power mode during that time and save a considerable amount of power. So in step 16, delete all the code from the while loop. Go ahead and delete the _bis_sr GIE from just above the loop. We're not using the I anymore, so go to the top and delete the volatile unsigned int I from the top of main.c. Then we need to add the following single line of code to the while loop. _bis, _sr, _register, and the parameters are LPM 3 bits plus GIE. So this single instruction turns on the interrupts and places the device in low power mode 3. Remember, this mode places restrictions on the resources available to use during the low power mode. The CPU, the M clock, the SM clock, the DCO, all of those are off. Only the A clock, which is sourced by the VLO in our code, is still running. That's a good thing, right? Because that's running our timer. You may notice that syntax has changed a little bit between this line and the one that we deleted. MSP430 code has evolved over the years, and this line is the preferred format today, but the syntax of the other is still accepted by the compiler. So at step 17, the entire main routine should look like what you see on the screen and in the workbook. That takes us to step 18. The status register bits that are set by the above code, the SCG0, that turns off the SM clock, SCG1, that turns off the DCO, and CPU off turns off the CPU. When the interrupt service routine gets taken, the status register is pushed onto the stack automatically. The very same status register value will be popped, sending the device right back into LPM3 without running the code in the while loop. This would happen even if we were to clear the status register bits during the interrupt service routine. Right now, this behavior isn't an issue, since this is what the code in the while loop does anyway. If your program drops into LPM3 and only wakes up to perform interrupts, you could just allow that behavior and save the power used jumping back to main, just so you could go back to sleep. You could jump in and out of a low power mode instead of jumping back and forth back to the to main. However, you might want to write some code in the while loop to actually run and be interrupted. So we're showing you this method instead. Add the following code to the end of your timer ISR. _BIC, _SR, _register on exit LPM 3 bits. This line of code clears the bits in the popped status register. More recent versions, by the way, of the MSP430 clock system, like the one on this device, incorporate a fault system and allow for fail-safe operation. Earlier versions of the MSP430 clock system did not have such a feature. It was possible to drop into a low power mode that turned off the very clock that you're depending on to wake you up. Even in the latest versions, unexpected behavior can occur if you, the designer, are not aware of the state of the clock system at all points in your code. We've all been bitten by it. This is why we spent so much time on the clock system in the Lab 3 exercise. So if you're not waking up from a low power mode, you need to go back and look at your clocks and what clocks you're actually expecting to be there. In step 19, the timer ISR should look like what you see in the workbook and what you're seeing on the screen in front of you. In step 20, build, load, and run the code. Make sure that the LED is blinking once every 3 seconds, and ours is. Halt the code and click the Terminate button to return to the Code Composer Edit's perspective. By the way, this code is saved in lab6a.txt in the Files folder if you're having any problems. In step 21, we can move ahead and take a look at the current that's being drawn. So I'm going to remove all the jumpers on J3, and I'm going to connect my meter as before. So we're getting, in between the blinks of the LED, we're getting 0.6 microamps. That's the value that we got. You should get something close to that. Here, just to make sure, I'll go ahead and click the reset button to make sure the code's running properly. 0.6 microamps. This is a huge difference. The CPU is spending the majority of the sampling period, those 3 seconds, in LPM3, drawing very little power. So remove the meter leads and carefully place the jumpers back in place. At the bottom of step 21, there's a graph of the current consumption. That would look something like what we see below. Our code still isn't generating quite this timing, but the DMM measurement would still be the same since it can only basically measure what's going on in the middle there. If you wanted to measure the actual current, you'd probably have to use an oscilloscope to do that. Now, right before step 22, the final step is to optimize the code for low power to remove the software delays in the interrupt service routine. We can use the timer to implement some of these delays and save even more power, but it's unlikely that we're going to be able to measure this with a DMM and not a sensitive happen so quickly. But we can verify that the current doesn't go back up. There are two in the timer ISR, one for the reference settling time and the other for the conversion time. So in step 22, the delay cycle statement should provide about a 40 microsecond delay, although there's likely some overhead in the no-op loop that makes it slightly longer. For 2 reasons, we're going to leave this as a software delay. First, the delay is so short that any timer setup code that we did would probably take longer than the timer delay itself. 2, the timer can only run on the A clock in LPM3. If we tried to run it at a faster rate, we'd have to use a different clock. We'd have to use that clock. It would use up more power. So that being the case, we're going to stay with that. At the speed that the timer, at that speed, at the VLO speed, the timer has an 83 microsecond resolution. So even a single tick is longer than the delay that we need. But we can optimize a little bit here. Change the statement shown below, the underscore delay underscore cycles, from 5 to 4. And that will reduce the specified delay to 32 microseconds from 40. In step 23, the final thing to tackle is the conversion time delay in the timer A0 ISR. The ADC can be programmed to provide an interrupt when the conversion is complete. That will provide a clear indication that the conversion is done. The power savings will be minimal because the conversion time is so short, but it's fairly straightforward to do, so why not do it? So what we're going to do is add the following ISR template for the ADC10 to the bottom of main.c. Again, this does the same thing by plugging in the address ADC10 into the ADC10 vector in the vector table. That takes us to step 24. Copy all of the lines in the timer ISR below, that's in the code below, copy all of the lines in the timer ISR below delay cycles 100 and paste them into the ADC10 ISR. In the timer ISR, delete the code from delay cycles 100 all the way through the P1 out and into with bit 6 line. At the top of the ADC10 ISR, add ADC10 CTL0 and equals the NOT of ADC10 IFG. That will clear the interrupt flag that occurs when that goes off. In reality, that's a single source flag and should clear itself, but it's never bad programming practice to go in and clear an interrupt flag. Step 27, in the ADC10 ISR, delete the P1 out and equals the NOT of bit 6 and the CCR0 plus equals 3600 lines. Lastly, we need to enable the ADC10 interrupt. In the timer ISR, add plus ADC10IE to the ADC10 CTL0 register line. So you can see that in the top line of the timer A0 vector. So let's look over that code real quickly. There's the timer A0, the timer 0A0 vector. There's the ADC10 CTL0, setting the reference, the sample and hold time, turning on the reference, turning on the ADC, telling it we want an interrupt, a short delay for the reference to settle. We turn on the encoding and start the conversion. We wait a period of time there and then return. In the ADC10 interrupt service routine, we clear the interrupt flag, disable the ADC conversion, make sure the reference and ADC are off, and read the conversion value. Go ahead and build and load the project. Make sure if you have any breakpoints in place, make sure you eliminate those and go ahead and run the code. We eliminated the flashing of the green LED. In this case, since it flashes too quickly to be seen, there's no way to see it. Set a breakpoint in the _BIC _SR line in the ADC10 interrupt service routine. And verify that the value in temp raw is updating as we expect it to do. And I'll put my finger on the top of the part. So there we go, it's working properly. Click the Terminate button to halt your code and return to the editing perspective. If you're having a hard time with the code modifications, you can find this code in the Lab 6B text file in the Files folder. So the summary here, our code is now as close to optimized as it gets, but there are many, many ways to get here. Different people would have taken different tacks to get to this point that are often just as valid as the next. Often, the need for hardware used by other code will prevent you from achieving the very lowest power possible. If you need your timer someplace else or you need something, this is the kind of cost-capability trade-off that engineers need to make all the time. For example, you may need a different peripheral, such as an extra timer, which costs a few cents more, but provides the capability that allows your design to run at the lowest possible power, giving you better runtime of years rather than months. So in step 30, we're going to remove all the jumpers on J3 and make our final current measurement. I'll hit the reset button, and we can see we have 0.6 microamps here. So that's what you should have. A graph of the current consumption would look something like what we have on the screen here. That may not seem like much of a savings, and you're certainly not going to see it on the multimeter. You would certainly see it on an oscilloscope, but every little bit counts when it comes to battery life. To quote a well-known TI engineer, every joule wasted from a battery is a joule that you'll never get back. So remove and turn off your meter. Speaking of saving the battery, and replace all the jumpers on J3. We're finished measuring current, and we won't be using the meter again. Go ahead and close the Lab 6 by right-clicking on it in the Project Explorer and selecting Close Project.